to finish. Should only take you an hour. It's composed of 25 true false. Again, if you know the quiz materials, you're going to do really well on that portion of it. It has 10 multiple choice. And both the true false multiple choice are worth 1 point apiece. Then it has 3 short answers worth 10 points apiece. And what I'm looking for there is just kind of brief statements. It's not going to take you a long time to do it. And then there are 2 kind of more longer essay problem type sets, which allows me to see if you actually know the information and can apply it. We're going to go through some examples today of what that would be like. Okay, so in addition to simply being able to know definitions and ideas, you need to be able to put it into use from a subject point of view. And so those last 2, which is worth about half of the test, 50%, will be essay short answer type things. Okay. In addition to, we're going to go through some problems today just to make sure everybody's kind of up to speed on what you might see and might find on the test. But we will have a Zoom review session at 5:30 tonight to 6:30. You should have gotten a link. Did everybody get a link to that? I sent out an email on Friday, I think, with the link. I'll send it out again, but you should have gotten a link to that. It is not mandatory that you go to that. It's simply if you want to participate in that Zoom meeting, you can do that. If you have questions, bring the questions to that meeting, and we'll spend time going through your questions and things like that. I'm not going to bring information to present. I'm just going to be there to answer any questions that you might have. Questions on the exam? If this is actually not in the middle of the semester, obviously, but I think it's a good breaking point for us because after we get done with this section where we're looking at chemical contaminant and sediment interactions, then we move on to more geomorphic hydrology type things, but we'll be using the chemistry throughout our discussion. So this is why we're going to have it. All right, so this is something that you might see on the exam, something like this, or at least you would, to be able to answer, say, true, false, or multiple choice, you might have to be able to interpret data that's related to this problem. The basic idea is you want to determine here, in this case, calcite, could be any mineral that we have, will undergo significant dissolution in river water that has the following characteristics. So what do I mean by dissolution? What are we looking at here? What type of reaction? Calcite's going to dissolve, yeah. So we want to see if it's going to, we have a crystal of calcite, very common mineral. What's calcite found in?
Calcium.
Calcium carbonate, rock type. Limestone? Yeah, okay. So we have limestone out there. We want to see if it's going to dissolve. So I've given you some things here. So it's always good to figure out exactly what I'm giving you. This is the concentration of the uncomplexed molar composition of these calcium in the carbonate. So we've measured that in the water. We've gone out in the water. We've found out what the concentrations of calcium in carbonate are, in the bicarbonate are. Carbonate, calcium carbonate. All right. This word's really important, right? We'll come back to that in a minute. Uncomplexed. So in the case of calcium carbonate, this guy could form complexes, right? It could form HCO3, the bicarbonate I just mentioned. It could form H2CO3, organic acid. So there's a variety of things that could form. So we're looking at the concentration of uncomplex form. And then down here, we have the activity coefficients for calcium and carbonate, and I've given you those. And then I've also given you the equilibrium constant K. Okay? So what I would like you to do kind of real quickly here, take a couple of minutes to do it. You can talk amongst yourselves as you would like to. Set this problem up. How would you go about solving this? You don't have to actually calculate it unless you want to, but at least set up the issue. How would you go about solving this problem? And I'll give you a few minutes to do that. Okay, we have some ideas of how we're going to approach this thing. Remember an index? Yeah.
Is it the saturation index?
Yes. So what's that saturation index tell us? Remember this thing? So here's our saturation index.
It tells us whether the solution is like saturated, oversaturated, or undersaturated.
Right. So it will tell us with respect to calcium carbonate, in this case, calcite, whether it's going to be saturated, undersaturated, or oversaturated. And that, from knowing that, we're gonna be able to determine whether we're gonna get calcite going into solution, or whether some of that calcite may precipitate, or they'll be balanced out. So this is our equation. What's K of the mineral here? What's that?
The constant,
It's a constant.
so it's the 4.9.
Yeah, so that is our equilibrium constant, right? And what's that really telling us? That's the amount of calcite that would go into solution under what conditions?
Equilibrium.
Equilibrium, but certain type of laboratory conditions.
It's like 25 degrees Celsius
Yeah.
in 1 atmosphere.
Yeah, so very controlled conditions in pure water. So we're not have anything else in the water, pure water, 25 degrees C, 1 atmosphere. It's the amount of calcium carbonate that would go into solution. Okay, so that's the laboratory. What's IAP?
Your actual data.
That's the actual data. Remember what that stands for?
Ion activity product.
Yeah, that's the ion activity product. So that's the real data here, right? We're going to go out in the field. We're going to measure the concentrations of barium and sulfate within the water itself. Now, as long as we always have calcium carbonate present, the equation kind of simplifies into this. If all that calcium carbonate got actually at some point dissolved, we'd have to include it as the denominator down there. We don't have to worry about it. It's always going to be calcium carbonate in this case. Why can't we use just the measured concentrations of barium and sulfate in this equation? Because some of it might be,
It's uncomplex.
yes, it needs to be uncomplexed, for one. So if we have some kind of complexation in this case, and instead of putting calcium carbonate up here, I used this slide that's already made up. But if it was complexed, then the activity would be lower than the actual concentration. So that uncomplexed is really important because that's what goes in here. That's how we figure activity. Here's our actual activity. This is how we calculate it. This is our activity coefficient times the concentration of the uncomplexed form, right? Okay. So what we want to do is we want to find this out. This has already been given to you, and actually that's already been given to you. You can just substitute them in for those two cases in the case of calcium carbonate or barium sulfate. So I've actually given you these two guys here, and so we'd have to multiply those things out. So this for this particular slide, 4.9 times 10 to the 9. And this is what we would do. This was your activity coefficient for barium. This was its concentration of the uncomplex stuff. So that goes in here. And then we're going to multiply that times the activity coefficient for sulfate versus that. Okay. So we're just taking this stuff. This is the activity of barite or barium. We're just going to move that up in here in these two places, and we can get our IAP. Then what's next? Once we have that, we substitute it back in up here, and we divide this by that. See how it works? Okay, in this case, given the numbers that I gave you, it actually comes out, once we take the log to the base 10 of that number, comes out to 1.28. So what's that telling us? Because I use log, this should actually be 1 in here. But 1.28, what would that say? Is it oversaturated, undersaturated?
Oversaturated.
It's what?
Oversaturated.
Oversaturated. Okay, so if it's oversaturated, what's likely going to happen?
It's not gonna have
Yeah, so it's gonna precipitate out of the water. And we're gonna probably form coatings and things on the channel bed and things like that, okay? So we're gonna get, if it's oversaturated, it may not do it real fast. We don't know how fast it's gonna happen, but it's gonna go towards precipitation. If it was undersaturated, what would it be? What would happen? Let's say it was minus 0.1 or something. Actually, since I'm taking the log, it'd have to be less than 1, but if it's undersaturated, it's going to dissolve. Yeah. So if it's not at equilibrium, it's either going to have to dissolve more to get it back into equilibrium, or it's going to have to precipitate some of that out to get it into equilibrium. If it's undersaturated, the water can hold more until it becomes saturated, right? So we're going to get dissolution. If it's oversaturated, it's going to precipitate. Change this value here because I use log. There's several different equations for the saturation index, and I just mislabeled this, but this should be 1 here when I have one. All right, so I will not ask you on the exam to bring a calculator and actually calculate this out. But I might ask you, hey, if you have a saturation index of 0.5, is it undersaturated, oversaturated? What are you going to expect to happen? Okay. Or if I tell you there's it is oversaturated, what's going to happen? It's an equilibrium. So being able to understand how you got this and what this index is telling us, because this is important in terms of trying to figure out whether we're going to have more stuff go into solution, we're going to have higher concentrations potentially of a contaminant. We could have lead carbonate here instead of barium sulfate. So barium high enough concentrations is actually toxic. So, yeah.
So would you ask us to do like a complex formula or?
I will not on the test, but I want you to know how to use the numbers. Okay, so here's another problem. A 2-stage, this is based on our EH-pH diagram. So we have down here pH, we have here our concentration of a particular cation. In this case, we're looking at zinc. And so the problem is here, if we are given a table like this, or a couple of diagrams. So here's our EH-pH diagram. So pH reducing versus oxidizing. And we collect water from a riparian wetland. So what's a riparian wetland? Do we all know what that is? So this wetland along the stream channel has a pH of 5.5 and an EH of minus 0.1. What's the dominant stable species of zinc likely to be, assuming that the system contains sulfur? So we know that sulfur is in the water, or in the sediments. We know what the EH and pH is. How do we determine, based on these diagrams, what our chemical species is going to be? How is zinc going to exist within the water? What do we have to do? Yep.
You go to the pH of 5.5, and then you go to the EH of negative 0.1, and then you meet them together.
Yep. So we're just going to plot that point on here. It's like Charles was mentioning, and that's where it comes out. So about 5 minus 1, and it plots it in the zinc sulfide. So how's it going to exist in that system? It's going to occur as zinc sulfide, which is a solid, right? So there will be some floating around there in zinc as zinc 2+. But overall, it's going to primarily occur as a solid within that stream system, given the EH and pH conditions of the water within that wetland. All right? So that's not too difficult to do. We can simply plot those numbers on the diagram. Now, if you were a geochemist and you're doing it, the hardest part of this is actually you have to create these DH-pH diagrams. They're always a little bit different given what's in the water itself. If you had other ions floating around in there and stuff, you're going to have slightly different shapes and stability fields for these species. But if we're given this, we can figure that out. Okay, everybody with me on that? Now let's take another one. We're going to take that same wetland and we're going to drain it. And if we drain it, we want to figure out what the dominant form, how this might influence the dominant form of zinc. Okay, so we're going to take that wetland, which we know what the EH and pH is. We're going to drain it for some reason, so those sediments get exposed. There's water's no longer in it. And we want to figure out what the dominant species is and what it might do to the concentration of zinc in the pore waters in those sediments. All right, so what happens if we take that wetland and we drain it in terms of EH?
It'll increase.
It'll increase. Why is it going to increase?
For water to dissolve it,
What's that?
because there's nothing to dissolve it, like, in concentration.
Yeah, but we're doing something else in addition, right? So if we take all that water away, we're exposing it to oxygen. And so we've now taken a reducing environment. So it was way down here, -1, so that's a pretty reducing environment. And we've exposed it to oxygen, and so this is going to go up, right? Okay, so that's most likely. But what else do we know about zinc sulfides? What happens to zinc sulfides in the presence of oxygen? Sulfides become, what's that process?
It's oxidation.
Oxidation. So they get oxidized, right? So the zinc sulfide, when it's exposed to oxygen, as pH goes up, it's actually going to become oxidized. It's not going to go under an oxidation reaction. Are you with me on that? So let's take a look at that oxidation reaction. And these are the ones I initially showed you. We've got all these sulfides. They do a similar thing. And pyrite's kind of the simplest to look at. We had iron sulfide. We hit it with oxygen in the presence of water. The cations come off in solution, and we produced the hydronium ions and became more acidic, right? So we released the cation and into solution, and we became more acidic. We created acid mine drainage if we get enough of this. In this case, we're taking sulfide or zinc sulfide, we're oxidizing it. The equation's a little different. But ultimately, we're going to get the same type of result. So we take zinc sulfide, we hit it with oxygen, we get zinc oxide, and then sulfur dioxide. So zinc oxide, solid or, yeah. So in this case, we're getting a solid, which, kind of said, hey, most of the time we get cations. It's still true, and I'll show you why. What happens to sulfur dioxide in the presence of water? Anybody know? Anybody guess? It forms a, it forms an acid. So even though we don't see the hydronium ions just kind of come up there and obviously increases the acidity of the water, decreases the pH. In this case, when we add water to sulfur dioxide, it should be a plus. We're going to get H2SO3, which is sulfurous acid. So we're still going to increase the acidity of the water. Same thing happens. Under acid conditions, so when the pH is low, what happens to zinc solubility? It goes up, right? So that zinc oxide, in the presence of acid, which is occurring during an oxidation, we're still going to drive the zinc up in the water column. So what we're going to do is we're going to move it from here to here. So this starts becoming more and more abundant, even though our initial product's gonna be zinc oxide. Okay? So this diagram kind of still works out. We're gonna drive it up. We're gonna, potentially, if we do enough of this, we're gonna change the species, but it's gonna be through oxidation. Okay, with me? The zinc is kind of a crazy element in terms of its oxidation chemistry. It actually can occur in multiple steps. A lot of times these oxidation processes aren't as simple as what we're showing here. There's different controls and things, and that's kind of why I put it up here. But we're gonna get the same basic result. In this case, it's oxidation in the presence of sulfate, and we form sulfuric acid instead, but it still lowers the pH, which increases the solubility of the cation in water. Okay. So, yeah.
I know you probably explained this already, but why does a lower pH increase metal solubility?
Yeah, so there's two reasons for that. In the case of adsorption, desorption, we can look at it that way. So when you have more and more hydronium ions in the water, so really low pH, because pH is kind of the negative of the concentration of the hydronium, right? We stick more of those hydronium onto the mineral surface or the oxide surface or whatever, and it gives it a positive charge. And so that positively charged metal can no longer take on the other cations, and so those go into solution. Okay. Same with cation exchange. If you get higher and higher hydronium concentrations in the water, it's the hydronium that goes and sticks and exchanges for other cations in the mineral surface, and so it increases the absorption.
Gotcha.
Okay. And then pH also influences the precipitation reactions. You just, at lower and lower pHs, you just get more of it dissolving. It's just more soluble at those levels. So in terms of trace metal, cations, and really other hydrophobics as well, every time we start getting acidic conditions, we're going to have more stuff go into solution because those minerals become positively charged. So pH is a really significant control on the chemistry of what species are there. So this is kind of a real real life problem. We could take these wetlands where we're going to have it in a reduced form, and if we drain it, we expose it to more oxygen. It doesn't only have to be zinc. It could be lead sulfide. It could be iron sulfide. It could be copper sulfide. A whole variety of stuff. We expose it to oxygen. We're going to oxidize it, and it's likely to go into solution or create acid volume drainage. So this draining can really have an important influence. All right, there's another process that is also good to recognize. Oh, I got this one. I thought I had it on here. What happens if we had manganese or iron oxides or hydroxides in that wetland? So we go back to this thing. Let's say instead of zinc sulfide, we were looking at iron. We found out that we had iron oxides and hydroxides in the wetland, and then we drained it. We've changed the EH, right? And what do we know about the iron and manganese oxides and hydroxides? They are sensitive to redox changes. So the redox sensitive. And if in reducing conditions in the wetlands, are they going to be soluble or insoluble? The iron and manganese is likely going to be in, to the extent, solution, right? Because under reducing conditions, manganese and iron oxides and hydroxides tend to go into solution. Certainly much more solution than they would be under an oxidizing environment. So in that case, if we had iron and manganese oxides and hydroxides, we drain it, we expose it to more oxygen, oxidation goes up. What happens to those iron, to the iron and manganese? It comes out. It precipitates. So we could actually, in that case, we might have higher iron and manganese concentrations in the reduced waters, and then once we drain it, and let's say it's still in the pore waters there, we expose it to more oxygen, we could actually form coatings or precipitates of iron and manganese oxides or hydroxides around the grains and over the particles and stuff like that. So we've gone just the opposite that we did here. So in reducing conditions, they're more soluble. The other thing to remember is that those iron oxides and hydroxides, they're really chemically reactive. They have really high surface areas, they got a high charge on them, and they're good scavengers. They just grab all the cations out of the water, the other cations out of the water. So if we dissolve, if we go into a reducing state and dissolve those manganese and iron hydroxides, oxides, everything attached to them also goes into solution, right? So all of a sudden we might have a case where it's sitting there, it's in the stream, it's exposed to water, to oxygenated waters. The oxides bound all these other things to it. And then maybe in this case, we dump it into a wetland, which is reducing. What's going to happen? They're going to go into solution and they're going to release all of the metals that are and other contaminants that are stuck to the surface. And it's going to become more bioavailable, right? So there's two very different processes here to think about. The influence of EH and oxidation on the sulfide minerals, and then the influence of EH on manganese and iron oxides and hydroxides, which could switch from being a precipitate to a solution or slight changes that we normally find in a stream system. Okay? All right. Questions? So on the exam, what you would see is I might give you a problem like that. If you have a certain scenario and something happens and it changes the EH or the pH of the system, what's going to happen in terms of solubility of a particular cation? Okay. So you have to know what's going on. All right, let's take one more example here before we quit. I talked about this site earlier in the semester. I don't know if you remember it. This is in New Mexico. It was the United Nuclear Corporation's Church Rock Mill Tailings Dam. And it was essentially at this facility, they created yellow cake. And then in 1976, it broke and all the stuff that spilled out went into Pipeline Arroyo, which then went into another stream system. This is the Arroyo itself. This is where the contaminants are. This is actually my master's thesis. So this is a real world problem here, guys. And in this case, what I'm asking you is that we have these very acidic solutions, pH about 2, gets dumped into the stream. It's got all kinds of radionuclides and other metals in it, metal cations. And the question is, how far downstream is this stuff going to make it? So here's the problem. You have this tailings dam failure. It has a pH of 2. It exhibits a concentration of radionuclides and toxic trace metals. Shortly after the event, here's your scenario. You get a call from somebody and they say, geez, how far downstream? This is going to flow into Arizona. Is it actually going to make it all the way to Arizona? What's likely going to happen to all this contaminated stuff as it's flowing downstream? What are the chemical reactions that are going to take place? And how's this stuff going to move along the system? State line's 50 miles away. Then he says, okay, this is what it's composed of. Equal quantities of sand, silt, and clay-sized sediments. So we know something about what's in the sediment. Lithologically, it's primarily composed of quartz. The sand-sized stuff, it's got some calcium carbonate in it. The silt's composed of quartz and feldspars. The clays are smectites 2-to-1. And then the sand-sized stuff appears to have iron oxides coating the grains. All right, so the question then, what are you being asked in here is, do you think it's going to make it to the state line in solution? All right, this is going to be something that you will receive a question like this on the exam. The first thing that you need to do is pick this question apart. Understand exactly what information you've been given and what the actual question is that I'm asking, okay? So as you go through this thing, you can start picking out important pieces of data and the question that you have to address. So the fact that the tailings pond had a pH of 2, that's important. We know what the chemical conditions was when it left the pond. It's the concentrations of the metals were orders of magnitude above background. So we know that the concentrations were really high, right? Okay. The question then is whether you think the toxic metals will reach the state line in solution. So that, it's kind of buried in the text, but that's the question. Whether you think or whether you can determine how if it's going to make it that 50 miles in solution, right? Now, in these questions, you will find there may not be any right answer to it. You could answer maybe either way on this particular problem, and if you argue based on good, sound geochemical principles, I would give you credit for it either way. What I'm looking for here is that you understood the potential chemistry that took place. So a lot of these questions are going to be very open-ended. Based on the information we have, we may not know precisely what's going to happen, but you can make an educated guess. Okay. All right, so next thing we know, primary composed of quartz with calcium carbonate. What do we know about quartz?
It's pretty unreactive.
Yeah, it's pretty non-reactive. So the sand-sized stuff's going to be pretty non-reactive itself. Quartz, feldspars, not going to react much. Why is calcium carbonate important? We haven't talked much about this, but calcium carbonate does what?
It dissolves.
What's that?
It dissolves.
It dissolves in acid, right? And what's it do to the acid solutions? It tends to neutralize it, yeah. So we have stuff in there then that's going to potentially could start neutralizing the acidic conditions that exist when the stuff first came out of the stream channel. All right, so that's pretty important. Then we come down here, we got smectites, 2-to-1 clays. Why is that important?
Those are like highly reactive.
Okay, they're highly reactive. So it's important to know we got smectites. And then the next thing we've got iron oxides. Why is iron oxides important? Yeah.
They're redox sensitive.
They're redox sensitive and they're also reactive too, right? So these are good scavengers. The clays are good scavengers. So we have stuff out there to which cations could actually absorb. They could absorb to the clay minerals. They could absorb to the iron oxides. All right. So take a minute or two. After you pick this thing through, you know exactly what I'm asking, and you've got these data, think about it for a minute or two and kind of come up with a decision on whether you think it's going to move downstream in solution. What's going to happen? What type of things are going to happen? Okay, got some ideas? What are some of the things that might happen here as the tailings hit the stream here?
I would say that initially the pH would be so low that it'd be hard for the cations in the solution to bind to like the material in the river. But once the pH reached the calcium carbonate and like was able to neutralize the solution more, maybe the contaminants, the possible contaminants in the solution would be more easily able to attach to the sediments, and especially the smectates and Fe oxides.
Okay.
So I don't think it would make it the whole 50 miles.
Everybody see it? Yeah. Good. So that would be the argument. Now, what you don't know, you could say, well, it's not going to make it all the way down there 50 miles. That's a very plausible explanation. You could say, well, it's going to depend on how much buffering actually takes place. So if there's not enough, maybe some of it's going to make it down in elevated concentrations at full distance. We really don't know based on the data that we have. But what Charles just said is exactly what I'm looking for here, okay? Initially, it's going to be in solution. We're going to have those high concentrations, but as it begins buffered, pHs go up. We're going to start attaching more and more stuff to it. Now, you can elaborate on that. You could say pH is a control on adsorption, desorption. So we're going to get more adsorption as pH becomes more neutral. We could say that pH is a control on precipitation. And so as pH goes up, we might start precipitating out some of these things as various constituent oxides or carbon. Okay, so you can actually get into the processes a bit. But overall, that's exactly what I was looking for. Right? There's other things that occur in here I wouldn't necessarily expect you to know. So as we kind of put this water in there, in the tailings piles, this probably has a pretty low pH. It's a reducing environment. So pH is probably going to go up too. So we're going to actually probably precipitate more iron oxides, which are going to grab things. But I'm not looking for that level of detail on the exam. So that's just all fun and stuff. All right, questions on this? All right, let's say we add something to it. Let's say that there's a little bit of calcium carbonate, but I didn't want it to make the state line. What would I do? What might I do immediately to try to remediate the situation? I could go get what from the street? What was that?
Limestone.
Limestone or lime. I could go buy a bunch of bags of lime at some nursery or Lowe's or something and go out here and start throwing lime in the system and actually try to buffer it much more quickly than it otherwise would, just based on the carbonates that's actually present, right? So I could do that. And in fact, in a lot of coal mines and places where we have acid mine drainage, that's exactly what they do. They actually funnel the leachate, the effluent, the acidic waters into an area. They dump lime in it, they mix it up, it buffers it, all the stuff precipitates out, and then they can release the water that's buffered and kind of cleaner back into the stream systems. Okay, so that's actual remediation techniques. Okay. All right, so that kind of gives you an idea of what I'm looking for. Not only how absorption, desorption, precipitation reactions are influenced by EH and pH and other parameters, but be able to take that information and apply it to kind of these conceptual problems. And the one thing I'm always going to assume is that if we drain an area, we're going to increase the oxidation. It's going to become more oxidizing, less reducing. And if you flood it, it's going to become more reducing, less oxidizing. Those pore spaces are going to be completely filled with water, and so it becomes more reduced. Okay. All right, let's stop there. So if you could make that meeting, I'll send out another reminder this afternoon. That's great. You don't have to attend. But if you get to tomorrow and you realize, oh, there's something I should have asked and I didn't, send me an email, and I'll try to respond to it.